So let us start the discussion on phase transformation. I have planned to finish this topic in 2 consecutive lectures. This is the first one. The objective of this lecture, initially I'll give you a brief introduction to phase transformation process. Basically you will try to understand the physics behind it, what is the mechanism of the phase transformation, a bit of mathematical detail also. And then we'll see the rate of phase transformation and the development of triple T diagram. This triple T indicates time temperature transformation diagram. Then we'll see how the microstructure changes with the help of triple T diagram at different cooling rates. And we'll see some of the very important heat treatment processes like annealing, normalizing, quenching, spheroidizing, and we'll also see the microstructural changes because of these different heat treatment processes. And obviously microstructure dictates the material properties, so at the end we'll see that the material properties, how they are changing because of this. So in this slide you can see some of the phases, important phases that we have already seen in iron carbon equilibrium diagram. Okay, so here you can see this is the austenite phase. I've told you earlier that this is the FCC structure. Here you can see this is the ferrite phase, and this one is the iron carbide phase or the cementite phase, which is the intermetallic compound, and it is orthorhombic in crystal structure. So these three, austenite, ferrite and cementite, you have seen in the iron carbide equilibrium phase diagram. But here you can see another phase that you can see over here, which is basically the carbons are sitting at the phase center and the corner atoms, so it is like an FCC, but some of the carbon atoms are basically trapped along these vertical directions here. So because of that, it's a BCT structure, basically body center tetragonal structure that happened, and these are generally very hard material, hard phase, and which is called the martensite. This particular phase we have not seen in the equilibrium phase diagram, but we are going to see this kind of transformation also happens in iron. Okay, so anyway, we'll see this phase also in this discussion. So now in the phase transformation there can be different kinds of phase transformations. Okay, some of the phase transformations are very simple diffusion dependent phase transformation that we can see in case of pure metals. Okay, that where there is no change of number of phases. Okay, if you consider a pure iron, then you see the phase changes occurs at very sharp points and there is no change of phases. Okay, you just take very simple example like when water will be converted into ice. In that phase transformation, basically water remains water, that means the H2O in ice also, so there is no change of composition and there is no change of number of phases because it was initially liquid, then it will be solid, but the number of phases remains same because of that transformation. So this kind of unary systems having this kind of simple diffusion dependent. Some of the other phase transformations of these kinds are like recrystallization, grain growth. We'll see these also in the second part of the phase transformation. What are these recrystallization, grain growth and all that. Now a bit complicated diffusion dependent phase transformation also happens where one phase will convert it into 2 other phases. So in that case the change in number of phases, of course, like in Eutectoid or eutectic reactions, you know that one phase, maybe the liquid phase, is converted into 2 solid phases in eutectic, or one solid phase is converted into two other solid phases in case of eutectoid. So these are a bit complicated diffusion dependent, and some of the phase transformations are also possible which are diffusion less. That means probably the transformation is taking place so fast that the diffusion process actually not initiated. Okay, so it's a diffusion less, and this kind of metastable phases phase transformation occurs because of that, and martensite is such a product. Okay, where you have seen just in the last slide that martensite, and this kind of a diffusion less phase that we can get if we cool maybe austenite very fast, we get this kind of thing. Now in the last topic that what we have discussed was the phase diagram, and that was equilibrium phase diagram, if you remember. So now in equilibrium, what was equilibrium? In this diagram you can see equilibrium means the change of free energy of any system will be zero if there is very small perturbation in the system. Even if you can make a very small perturbation in the system, you will find that there will be no change of free energy. This is what is called the stable equilibrium. Okay, and here you can see there may be multiple number of stable equilibrium stages, and among them which one having the lowest value among all these minima is called the most stable equilibrium, and all other minimas are called the metastable states. So suppose one equilibrium system is there and you are changing its environment. Changing its environment means you are changing maybe the temperature, you are changing pressure, or whatever that may be. Because of the change of its surroundings, the system may go to another equilibrium phase, and this thing will happen only if in the second case the free energy is less. That means the system always try to move in a direction such that its free energy will decrease. That means the final free energy because of a transformation will always be less than the initial free energy. Okay, so this is what is the spontaneous process. So any spontaneous process, the change of free energy, that means final minus initial gives free energy, is always a negative quantity. So this is the basic information that we have to know because in transformation this has a big role. So in the equilibrium phase diagram that we have already covered, we have seen that was equilibrium. In the equilibrium diagram we have never seen that time was there, the temperature was there, composition was there. We have seen different kind of transformation, like austenite is transformed into pearlite at eutectoid composition at a particular eutectoid temperature, but how much time it will take for this transformation, that was not there. Or in the eutectic reaction, liquid will be transformed into ledeburite at the eutectic temperature, at the eutectic composition we have seen, but we have not seen that how much time it will take to transform into ledeburite. So actually in the equilibrium phase diagram, the idea was there ample amount of time has been given so that it is basically quasi-static process. That means a very slow process, and the cooling rate is very slow, such that at each and every stage it can adjust or accommodate itself such that the diffusion is always taking place, because the time you are allowing to adjust itself continuously. So it's a very slow process, and if the process is very slow, is kind of a quasi-static, then the phases that we have seen was there in the equilibrium phase diagram. But practical scenario is different. The process may not be so slow. The process actually is quite fast. So if the processes are respectively fast, then what kind of transformation will take place? What kind of microstructure will get? Okay, so that we are going to see in this particular chapter. So time is now a very important parameter, okay, or in other words the reciprocal of time, which is called the rate of transformation, that we are going to see. So kinetics means the time taken by the transformation to go to completion. So this is the main thing that we want to know here, or in other words we want to calculate what is the rate of transformation, okay. Then we'll see obviously some of the transformations are very slow, and if the transformations are practically, some of the transformations are very slow, but maybe for the economic production in the unit, in the industry, we may require to accelerate that transformation. So we'll see that whether really we can accelerate that or not. Or in some cases we find that the transformations are very fast, and we do not want that kind of transformation. So our objective there is to suppress the transformation. So we'll see that whether all the time that is possible or not. In some cases maybe these are possible, some cases not possible. So these are the important thing. When we know the kinetics very well, then this kind of manipulations we can do. So in a nutshell, basically we want to control this transformation process. So we want to control maybe the Eutectoid reaction. We want to control, if we can control, then we can control the structure of the material. Structure means the microstructure of the material, and if we can control the microstructure of the material, and you know that mechanical properties are related to the microstructure, so we can control the mechanical properties, okay. So kinetics is influenced by two important parameters. One is the free energy change, another one is the nature and mechanism of the transformation, okay. So let us take a very simple example of a transformation, like a solidification of a liquid, suppose, is converted into a solid phase, okay. Now in this transformation process, you can see if we plot this in the y-axis, it is the free energy, and in the x-axis we have plotted it is the temperature, and this point is the melting point, suppose, okay. So this point is basically the melting point. So let's take a pen. So this is the melting point. So this is Tm, okay. So this curve is corresponding to liquid, and this curve is corresponding to solid, okay. Now you see, if the temperature is below the melting point, then what will happen? That if it is below the melting point, which one is the stable state? You can see the solid is the stable state at this temperature. So definitely the process will go in this direction, from liquid to solid. So this is what is the direction of the process. Now the solidification process, so definitely will occur if the temperature that you are maintaining has to be less than Ta on the melting point, okay. Now you see that this gap is gradually increasing. If the temperature you keep at this temperature, you see this gap is large. This gap is large means the delta G is large. Delta G means the change of free energy, which is large. So definitely if the change of free energy is large, then solidification will be quicker, the rate may be the higher, okay. So this kind of intuitive idea we are getting from this graph. But if the temperature on which you are keeping it, if it is very close to melting point, then you find that this is very small, so it is expected that probably the cooling rate or the solidification rate will not be very high. But at a sufficient amount of undercooling or this supercooling, you will find that this will be higher. So these preliminary ideas that we are getting from the consideration of the free energy change. I think this concept is clear, okay. Now let us see what is the mechanism of the solidification. Okay, the mechanism of any transformation process. Solidification is one of the example where liquid is converted into solid. Okay, but it is also applied from one solid to other solids, or one solid to another solid. Everywhere it is applicable. So the nature and mechanism of the transformation can be considered into two parts. One is its nucleation. You can see initially, suppose this is a liquid, the whole thing is a liquid, and you see when you are keeping it at a lower temperature than the melting point, then what will happen? It will gradually solidify. Now if we want to divide that solidification process closely with time, initially what will happen, that in some of the portions you will find that small solid particles will form. Okay, and these solid particles will gradually grow, and after reaching a critical amount they will further grow, and ultimately a polycrystalline solid will form. So it has parts like nucleation. Initially these are called nucleus. Some nucleus particles will form, and then those nucleus particles will grow, and ultimately this is called the growth. And this is what is the mechanism of a transformation, any transformation. So there are two parts. One part is called the nucleation, another part is called growth. Now in the nucleation part, actually what happens, that initially at different position some solid particles are trying to form. Okay, trying to form means, what we mean by a particle? Particle means it is collection of some atoms. That's all. This is collection of some atoms. This is called a particle. So what is there within this small thing is like this. So this is a particle where basically these are like atoms. Atoms are present within a particle, and these atoms are basically arranged in a crystalline order. Okay, a definite crystalline structure. So this is what is this particle. So particle is collection of few atoms. Now what will happen, that depending upon the change of its free energy, or depending upon the change of surface energy, we will see that after reaching a particular size, suppose when the particle will reach to this size, then the further increment of the size will always reduce the total free energy of the system. Then it will automatically grow. But it may possible that now the particle size is this, and if the particle size is increased, if the free energy is increased, then what will happen, this particle again go into the liquid. So this particle will not remain there. So that means a particle once formed, which is a solid, but it has two possibilities. It can again go into liquid, or the particle will gradually grow. Particle will gradually grow into as a solid. So two possibilities are there. So when it will go into liquid, so actually what is happening, that up to a critical value or up to a critical radius of the particle, we cannot say that if this size will definitely grow. Okay, below this critical size, it has two possibilities. It can again go into liquid, or it can grow. So up to reaching this critical value, these particles are called embryo. As if they are in the embryo stage, they can again go into liquid, and or it can grow. But after reaching this critical size, after reaching a critical size of the particle, definitely it will grow. So when it will reach that critical size is called a nucleus. That means the nucleation has been completed. And once the nucleation has been completed, then in that position definitely the solidification will grow. Gradually that particle will grow. Okay, so it is not that all the points that you can see is going to grow. Okay, they may be in the embryo stage, but once they reach the critical size, then definitely they are going to grow. Now the nucleation process can be of two kinds, like it can be homogeneous nucleation or it can be heterogeneous nucleation. One thing you have understood by the time that suppose in a container some liquid is there, suppose water is there, okay, and you are keeping the temperature of the container very low because your objective is to make ice out of it, okay, or you want to solidify this one. So that is why what you are doing, you are keeping the temperature of the container below melting point, that means below 0 degree in this case. So now if you keep it at minus 5 degrees centigrade or if you keep it minus 20 degrees centigrade, the nucleation very much depends on at which temperature you are keeping it. Already we have seen, because if you keep it at minus 20 degrees centigrade, then the free energy change will be large, so expected the nucleation rate will be high. But if you keep it at minus 5 degrees centigrade, since the undercooling is small, so the free energy change will be small, and that is why rate of nucleation may be smaller. Okay, that we have understood. Now the question is that whether all the positions in that liquid having the same probability of forming nucleation or not. If all the points in the container, that means all the points in the phase, in this case that is liquid, all the points in the phase having the same probability of forming nucleation, then that kind of nucleation is called homogeneous nucleation. But suppose in this particular example, it is quite clear that this wall, the container having very low temperature, so chances that this position the nucleation will be at a higher rate. So probability of forming nucleation close to the solid surface is large, right? That means all the points in the phase do not have the same probability of nucleation. So if this is the situation, then it is called non-homogeneous. Okay, so nuclei of new phase form uniformly throughout the parent phase, then it is homogeneous, and nuclei form preferentially at structural inhomogeneities, insoluble impurities, grain boundaries, dislocations, and so on, then that means there will be some preferred sites where the chances of nucleation will be more. Generally, what are the positions where the chances of nucleation will be more? If there are some certain defects in the material, so if you know that defects having the higher free energy, so these are the positions where the chances of nucleation will be more. Okay, that means they are the preferred sites. Okay, so the nucleation will be heterogeneous, not uniformly. Okay, now try to understand this nucleation process through a very simple modeling of a particle, considering it to be a sphere. So let us take an example. Suppose this is a liquid region we are considering, and let us consider again that simple kind of a transformation, that is liquid is converted into a particular solid. Say this solid is this beta phase. Okay, so liquid is converted into solid phase, a solidification process. That's very simple solidification process, and consider the size of the particle is a sphere. That is again an assumption. The practical size of a particle can be very complicated because this is like that. So let us consider it's a sphere for simplicity, so that we can just get some mathematical deductions, and that will be very simpler. But overall, by this analysis, we will get some idea about this. So let us consider at a particular stage this particle having radius r. We do not know whether this r is some critical or not. That means we have just explained that if it is a critical, then after that definitely its radius will gradually increase. But if it is less than the critical value, then it can again go into liquid. Okay, so let us consider this is a particle that has been formed of radius r. Now in terms of energy, tell me, initially there was no solid, okay, it was liquid. Now you are putting this system in a temperature which is below the melting point, and because of that solidification has been started, and suppose at a particular point this particle has been formed. Now because of the formation of this solid particle, of the second phase particle, you tell me that what are the changes has occurred. So first of all, this solid in terms of energy, if we say, since at this position initially the corresponding to this volume liquid was there, but now corresponding to this volume solid is there. And what is the change of phase energy, phase free energy? If we consider the phase free energy change is delta G that we have just explained per unit volume, then this multiplied by this volume will give you the free energy change because of phase change. Clear? And tell me, this quantity is a positive or a negative? Definitely this is a negative quantity, because of formation of solid the free energy decreases, because at a lower temperature solid is a lower free energy state. So per unit volume, this is what is the gives free energy corresponding to the phase change multiplied by the volume of the solid particle. So this much of energy will gone down because of the solid phase formation. Now what are the other kinds of energy change? Initially when there was no solid, there was no free surface, there was no interfacial surface. But now because of the formation of this solid, you can see between the solid and the liquid a surface has been produced, and this solid liquid interface was not previously when there was no solid. That is why corresponding to this surface some free energy is required. So what is the change of that free energy because of the surface? That is called the surface free energy, and that surface free energy change will be positive because previously it was not there. Now that surface is present. So if that surface energy per unit surface area is gamma, which is basically the surface tension multiplied by the surface area. What is the surface area? That is 4 pi r square. So this quantity, remember, is a positive quantity because surface energy will increase, and this energy is a negative quantity because delta G is a negative quantity. Okay, so what is the net change of free energy? So net change of free energy is the ultimate thing. Whether this process from liquid to beta, this transformation will take place or not will be decided based on what is the net change. Okay, so that we can see over here. And remember, we have explained it with a very simple example of transforming from liquid to a solid phase, but this is also applicable for the transformation like Eutectoid transformation, that austenite is transforming into ferrite and cementite. Okay, the basic principle is remains same. Now degree of undercooling or supercooling already we have understood, because that is what is the temperature at which you are keeping it. So obviously the temperature at which you have to keep it is below the transformation temperature. In case of solidification process, below the melting point. And if you keep it quite below the melting point, then the degree of supercooling will be very large. So that is why the free energy chain will be large. So the idea is the driving force to nucleate increases as the delta T increases. What is delta T? Delta T is that degree of supercooling or degree of undercooling. Okay, so it is the driving force for the nucleation process. For small supercooling, slow nucleation rate. Okay, so if you keep the temperature close to melting point, so small amount of supercooling, then nucleation rate will be less. And if it is a large supercooling, so rapid nucleation will take place. As simple as that. Now you see the process that I have just told you. Here you can see the blue graph correspond to the phase change free energy. Okay, so the phase change free energy is this one. So this is corresponding to the phase change free energy, okay, and multiplied by the volume, and this quantity is a negative quantity. And here you can see with the increase of r to the power 3, basically it is varying. And how this is varying according to this line. Okay, on the other hand, you see the surface energy. As you increase the radius, it is varying with the square. So how the surface energy, and that is positive, how it is changing. So what is the net change? Net change is this plus this. One is positive, another one is negative. So summation is according to this green line. Okay, so this is how it will vary. Now you observe about the total free energy change. Observe what is happening about the total free energy change. What we know, that actual transformation will always takes place if the free energy change decreases. Okay, so here you can see up to a particular radius, this x-axis corresponds to the radius of the second phase. So up to a particular radius, you see with the increase of r, the net change of free energy is increasing. That means within this region it is in the embryo state. Within this region it is in the embryo state. Okay, but after reaching this point, after reaching this critical radius, this is what is the critical radius. After reaching this value, you see if one atom get into that particular particle, so radius of that particle will increase, means its free energy will decrease. And what will happen? Further and further it will decrease as the radius is increasing, and that is favorable to the system because the free energy is decreasing. So that is why the solidification process will take place, and ultimately the whole liquid will be converted into solid. So, but the critical radius has to reach. Okay, after that this process will automatically happen. So this process up to this much is called the nucleation, up to reaching the critical radius. Okay, so here you can see what is the effect of temperature. I have just told you, if you consider that say this is at a temperature T1 and say this is at a temperature T2, definitely both the temperatures are less than melting point temperature. Okay, so in this case at T1 you see this delta T is respectively small. That means your undercooling is not very high. So if the undercooling is small, that means you are very close. If you're this is melting point, and this is what is say T1, and maybe this temperature is say T2. So here you can see close to Tm, so this undercooling is small basically. This difference, that is T1 minus Tm, is called undercooling or the supercooling at this temperature. So here the free energy change is small, but it is expected that here the nucleation rate will be high, and that you can see in terms of the radius of the critical radius of the nucleus, that when the T1 is larger, that means close to the melting point, then you see that the critical radius is larger. So to nucleate, the larger radius has to reach, and only after that it will grow. On the other hand, you see that if it is T2, that means the degree of supercooling is very large. In that case, critical radius is very small. That means after reaching a small radius, it will grow. Okay, so definitely the effect of temperature you can understand in terms of critical radius also. And this is the expression of the critical radius. You can see it depends on the surface energy, that means the surface tension. It depends on the latent heat of the fusion or solidification, depends on the degree of supercooling and the melting point temperature in this way. Okay, it is very simple. The derivation is not very difficult actually. Simply from this equation, summation of this plus this, so this expression plus this expression, then you will get the equation of this curve, and if you find the derivative equal to 0, you will get this relation. Now in this case, let us try to see what is finally the nucleation rate. Okay, so nucleation rate as a function of temperature, if we want to see, it is very clear that if the degree of supercooling, here you can see this is the melting point. Now if your temperature at which you are trying to transform it, suppose you are trying to transform it isothermally, so if the temperature is here, you see that as you decrease the temperature, then what is happening? As you decrease the temperature, then the nucleation rate is increasing. Nucleation rate is very high. Okay, as you decrease the temperature, you see the nucleation rate is increasing, which is expected. So this is according to this kind of an exponential relationship. The frequency of attachment, that is also very important. Here you see within this line, within this curve, basically consider this is basically the particle, the solid particle that has been formed. Okay, and you see within that it is a crystalline structure. Now after reaching the critical radius of nucleation, what is required for the further growing? These atoms which are almost in the similar fashion, so you see that some of the atoms are exactly in a similar fashion and will cross the boundary and go into the solid particle, right? And then its radius will grow. So this is what is the idea. So to move these particles from one region to another region and ultimately go into the particle, this process is taking place by the diffusion. So it is not only the nucleation taking place because of the undercooling, free energy change and all that. The diffusion is another thing that is important, because it has to overcome certain energy, it has to overcome certain resistance in terms of viscosity to go into the solid particle. So that diffusion rate again depends on the temperature. If the temperature is very high, then diffusion will be high. If the temperature is very low, diffusion will be less. So this is something kind of opposite phenomena that is happening. So higher temperature is also required to come more and more particle and join into the more and more atoms and join into the particles to form the solid to grow. So here you can see that this particular curve indicates how the these particles are attaching into the into this particle. These atoms are basically attaching into the particle and trying to form the nucleus. So two opposite phenomena here you can see. So frequency of attachment will gradually increase if the temperature increases. Okay, but definitely dominating part is this one up to a certain range, because if you plot both these cases, that the number of stable nuclei form and frequency of attachment Vd, and what is their combination? The combination is like this. So this is what is the combination. So this is ultimately the nucleation rate. So this red line that I have just drawn is the net nucleation rate. So you can see up to this much, it is basically the degree of undercooling dictates the fact. If the degree of undercooling is large, then nucleation rate is more. But after reaching a certain value, you can see the diffusion is also very important, because now the temperature is so low, below which the temperature is so low, then this diffusion will not take place, or the frequency of attachment will be very, very low, and that's why the chances of forming further nucleus will not be possible. Okay, so that is why up to a certain temperature, definitely degree of undercooling dominates in the nucleation rate. So this is what is the nucleation rate curve. Clear? Now the second part of the process is the growth, and growth is what, after formation of the critical radius, if more and more atoms join into that, and the radius of the nucleus gradually grow and ultimately solidify the whole thing. So growth is basically depending upon how the atoms are moving from one place to another place, and that is very important. So diffusion is the dominating phenomena here in the growth. So rather, only thing that is important is the diffusion, and already you know diffusion is a very much dependent on the temperature. And how it is depending on the temperature? Definitely with the increase of temperature, diffusion rate is more. That is why growth will also takes place like this. You can see with the increase of temperature, growth is increasing, because the diffusion will increase if you increase the temperature. Okay, so if you see the nucleation rate is like this, this is what is the nucleation rate, and the growth is like this, because it is diffusion dependent, and diffusion increases with the increase of temperature. This is what is the melting point or the transformation point, whatever you say. So what is the combination? So combination is required because we ultimately want to find out the net transformation rate. So this rate, net transformation rate, is the combination of nucleation and growth, because this is what is the two processes by which the net transformation takes place. So this blue line indicates the overall transformation, and you can see the overall transformation is like this. Up to a certain level, it is the nucleation which dominates, and after that it is, if the temperature is very, very low, then diffusion will be very, very low, and that is why net transformation rate will decrease. Okay, so this is what is the net transformation rate. So this blue curve is very, very important, because now we, in the further subsequent section, we are basically concentrate on this blue curve or the net transformation curve. Now let us go into our iron carbide diagram, which was equilibrium diagram, and let us take one very important transformation process that has occurred at eutectoid composition at eutectic temperature. That is what austenite is transformed into pearlite, right? Austenite at 0.76% or 0.8%, whatever you call, that will transform into ferrite and cementite in the form of lamellar structure, which is called the pearlite, right? So now if we concentrate at this particular transformation, why we are concentrating at this particular transformation? Because this is a very important transformation regarding steel. So we know that this region is corresponding to steel. So basically this is corresponding to eutectoid composition steel. That means 0.76 or 0.8% carbon. Okay. Now in this transformation, what is the final product? The final product is pearlite. What about the transformation rate? I have told you the transformation process is very, very slow, then only you will get this kind of a pearlite. Okay, now we'll see that how we can get a time temperature transformation diagram out of it. Now here this is an experimental result of how much time it will take for the complete transformation. Okay, suppose you take a particular mass of material and you are putting it at a particular temperature, and definitely that temperature will be less than the transformation temperature. Suppose the Eutectoid transformation temperature TE, Eutectoid is say 727 degrees centigrade. Okay, this is the transformation temperature. So now here is austenite, and what you have done, you just put this at a temperature say 650 degrees centigrade. So definitely 650 degrees centigrade is a temperature below this temperature. So at this temperature you are keeping it for a long time, and you observe that how much time it will take to transform this austenite into pearlite, that means ferrite and cementite. Okay, so we want to see how much time it will take. So we are considering this transformation. Let us consider we have taken it as 0.8% or 0.76% carbon. So Eutectoid transformation. So that we are observing. So we have taken certain amount of austenite and we are doing this experiment. We are keeping isothermally, we are observing, so we have kept it at 650. So this curve is corresponding to say 650 degrees centigrade. So throughout the temperature is 650 degrees centigrade. It's a kind of isothermal transformation. Okay, temperature remaining constant. We are not changing the temperature. So what will happen? You will observe that up to a certain time, the x-axis is basically indicating the time, and since the time may take very long, so it has been plotted in a log scale in the x-axis. So up to a certain time it will take for the nucleation process, and after that the growth will start, and gradually you will find the fraction of a few portion will be converted into pearlite. Okay, so gradually that portion will increase, and ultimately the whole thing will become pearlite. Okay, so you are basically noting in the y-axis is the fractional transformation. Maybe 20% has been converted, 20% austenite has been converted into pearlite, 50% austenite converted into pearlite, and here 99.9% austenite converted into pearlite. Okay, so this curve basically indicates the fraction, how much has been converted over time, how much time it will take to transform completely from full austenite to full pearlite. So I think you have understood what is this experiment and how we are getting this graph from the experiment. Okay, and this particular graph can be expressed in this form, exponential kind of, and this is you can see a S curve, or this kind of a S kind of a curve is observed, and by convention the rate is considered as corresponding to 50% transformation. How much time it will take, simply reciprocal of that is considered as the rate of transformation for this transformation from austenite to pearlite. Okay, and this particular equation is called the Avrami equation that we get from this experimental result. Okay, now suppose a similar kind of transformation like austenite to pearlite, suppose we are considering at T is equal to 675 degrees centigrade. Okay, so this is an isothermal transformation curve. Here basically the fraction that has been transformed, here it is the time plotted in log scale. Okay, so how much time it will take we can see. So where the transformation actually starting, maybe the transformation is starting here at this point. Okay, and this is corresponding to a curve 675 degrees centigrade. So here you go to the 675 and you identify the point corresponding to 675 where, so you draw a line from the temperature 675 and you just draw a line vertically where in the time axis, here it is the time axis, same time axis, how much time it will take to initiate the growth, maybe fraction that has been started, maybe say 0.1%, say 0.1% has been transformed into pearlite. So this is the point which we are calling as the start of the pearlitic transformation. Okay, and when it will finish, the transformation finished maybe at 99.9% is done, that we are calling as pearlite transformation finish. That means austenite to pearlite transformation finished, but throughout temperature is 675. That is why we have identified these 2 points corresponding to 675. Now we can do the same experiment but at a different temperature. Maybe we can do the same experiment at 600 degrees centigrade, and if you do that experiment, what you are expecting? The curve will shift in the left side or the curve will shift in the right side corresponding to 600 degrees centigrade maybe. Since 600 degrees centigrade is a lower temperature, so what about the transformation? If you remember the transformation curve, how it was, this was the transformation temperature say, and the transformation curve, if you remember, is like this. Now instead of 675, if you are here at this temperature, what is your expectation? The transformation rate is, here it is the rate, in the x-axis it is the rate. So rate is high or less with respect to, this is say 675 and this is say 600. So at which temperature the rate is more? At 600 the rate is more. If the rate is more, then obviously the time required for the transformation will be less, right? So 600 is probably will be like this. Probably it will start here and it will end here. So this kind of a curve probably you are getting corresponding to 600 degrees centigrade. At 600 degrees centigrade the curve. So what is the starting point? You draw this line and you draw this line, you'll get a point where the transformation starts at 600 degrees centigrade, and at 600 degrees centigrade when the transformation ends, you just draw a line corresponding to that, you'll get at this point the transformation end. So in this way, if we do the experiments at different temperatures, say 700, 650 and all the temperatures, we will get some starting point corresponding to those temperatures that we can simply project from this diagram. And if we join all these starting points, then we will get a curve like this green one. This is called pearlitic start curve or 0% pearlite. That means pearlitic transformation started. It's 0.1% pearlite. Okay, and this curve, red curve, corresponding to when the transformation ends. So in this way, at different temperatures, we can also plot all the points, and if you join those points or if you find the locus of the end points, you will get the pearlitic end curve. So this diagram is what is called the time temperature transformation diagram, where what you can see, this is the starting curve of the transformation. Here you will see this is the finishing curve of the transformation. What are the axes? Axis is temperature in the y-axis and time in the x-axis and temperature in the y-axis. So triple T diagram, that we can see the time is there in the x-axis, temperature, This T is temperature. Temperature is there in the y-axis, and these curves are the transformation start and transformation finish. So this is basically the transformation curve. So this is corresponding to the transformation. So time, temperature, transformation diagram. So this diagram is called time, temperature, transformation diagram. So in this case, which transformation we want to say? In this example, we have seen the transformation of austenite to pearlite. Clear? So this triple T diagram are actually forming by this kind of experiments and by projecting those in the temperature time. Now, if you see that the Eutectoid transformation rate, how it is changing with delta T. Already we have discussed, but still let us try to see it once again, that what about the microstructure if you increase the degree of supercooling. That means if you do it at 675 degrees centigrade, and if you do it at 600 degrees centigrade, then what about their microstructures? In this case, in both cases, we are going to get pearlite. Here the pearlite start, and here it will be end of the pearlite. So you'll get pearlite here. Here also we'll get pearlite if this transformation takes place. But what about their structure? We can see that the structure will be like this. What about the rate? If you see the rate of transformation, if you remember, what about the rate of transformation? And here it is the temperature. Suppose this is the transformation temperature or the Eutectoid temperature. Okay. Now, what is the nucleation curve? If you remember, the nucleation curve is like this, right? What about the growth curve? Growth curve was like this, right? So this is the nucleation, and this curve is corresponding to the growth. Now you see that suppose you are at this temperature. This temperature is 675. Eutectoid temperature is say 727. Okay. And we are comparing these two cases. Now you see at this temperature, which is 675 degrees centigrade, which is close to this one. So what about the degree of undercooling or delta T? So delta T is small. This delta T is small because degree of undercooling is small, corresponding to 675. What about the nucleation rate? Nucleation rate is small or large? You see the nucleation rate is this much. And what about the growth rate at this temperature? The growth rate is this much. So you can see at 675 nucleation rate is small, but the growth rate is large. So if the nucleation rate is small and the growth rate is large, then what will be the microstructure? Definitely nucleation rate is small means small number of nucleus will form. And if the growth rate is large, that means that nucleus will grow very fast. So what will happen at the end? At the end, the structure that you are going to get is large size grains, and few number of grains will be there, and the grains will be in large size. Few number of grains will be there because the from the few nucleation sites, the nucleus will grow very fast. That is why large size grains you will observe. Coarse pearlite you will observe. Okay, so the pearlite structure you will get definitely, but the pearlite will be the coarse pearlite because the nucleation rate is small and the growth rate is very high. But now suppose you are at 675 degrees centigrade, where you can see your growth rate is small but the nucleation rate is high. If the nucleation rate is high, then what will happen? Many nucleus will form, and they will grow gradually. The growth rate is not very high. So what will happen? We will get fine grain structure. So here you will get the coarse grain at higher temperature, and at 600 degrees centigrade you will get a fine grain structure. So you will get the fine pearlite. Okay. So microstructure will depends on at which temperature you are transforming. Here we are talking about the isothermal transformation. That means the whole transformation is taking place at a constant temperature. It can be 650, it can be 600, and you can see depending upon the temperature of the transformation, its microstructure is changing. And you know that if the microstructures are different, their mechanical properties are different. Okay, so if it is a fine grain structure, that means it's a strong material. If it is a coarse grain structure, respectively softer material. Okay. So you can see this isothermal transformation of austenite. Suppose this is the cooling curve. A, B, D is the A, B, C, D is the cooling curve. Initially, suppose you have heated it into the austenitic range, and then gradually you are cooling it. Suppose initially you are cooling it very fast up to point B, then you keep it at a constant temperature. Maybe in a salt bath you are inserting it for a long time. Then what you will observe? It will transform from austenite to pearlite. Okay, so here you can see the austenitic structure. Maybe at point C, no pearliting has been started. This is corresponding to the 50% transformation. Some of the pearlite has been started. And what kind of nucleation is this? This is a homogeneous nucleation or a heterogeneous? Definitely heterogeneous. Why? Because the grain boundaries are the preferred region. Chances of nucleations are more there. And you can see along the grain boundaries they have started transformation, right? So finally the whole thing will be converted into pearlite. Okay. Now let us see what will happen if it is not eutectoid still. That means if the composition is not 0.76 but if it is more than that, that means hyper eutectoid. Say on composition that is 1.138% of carbon. What is the final structure we have seen in the equilibrium phase diagram? First tell me. In equilibrium phase diagram we have seen the pro-eutectoid phase will be cementite, right? So before eutectoid some amount of carbide will form, and after that the remaining portion will be converted into pearlite. So final structure in this case austenite will be transformed into some Fe3C, which is the pro-eutectoid phase, plus pearlite. So this is what is the final structure that we'll observe. This is the pro-eutectoid cementite. In pearlite also basically it is alpha plus Fe3C, but these alpha plus Fe3C are in the lamellar structure in the pearlite. So this is what is the transformation that will take place if it is a hyper eutectoid steel, that we have seen already in the equilibrium phase diagram that you can see over here. Now you see what is the transformation curves. What are the transformation curves will be there. Here you can see the pearlitic transformation curve, the green one, the red one, pearlitic transformation end, green one, pearlitic transformation start, and one extra transformation curve you can see which is corresponding to pro-eutectoid phase transformation, which is the cementite in this case, right? So this is the cementite transformation start curve that we'll observe here by the blue line. Okay, and I have just overwrite it with the red one. So this is what kind of transformation you will observe. Again, their structure, whether they will be fine or a coarse, everything you can judge from the transformation, basic transformation rate curve. So this is the diagram, the whole time temperature transformation diagram over the whole range you can see here, which is corresponding to 1.13% of carbon. And here you can see, here it is the austenite, and here it is austenite plus C indicates the cementite. Okay, because pro-eutectoid phase at hyper-eutectoid still, you know, cementite will be there, right? And this austenite will start transforming pearlite from this curve, and it will end at this one, the green one. Okay, and this dotted blue one is the 50% line. Okay, up to this part you have understood, because this region corresponds to the pearlite, this region is the pearlite. Okay, but below that you see this particular curve is a different kind of a structure. Here you can see, which is called the bainitic structure. Okay, this B indicates bainitic structure. This particular structure is not an equilibrium structure, and we have not seen, that is why in the phase equilibrium diagram. So bainite structure, we'll see bainite structure later on, but right now you see this region is the bainite, this region is the bainite. So similarly, bainite is a transformation, so that means austenite will be transformed into bainite. So this is the austenite to bainite transformation start, and this is austenite to bainite transformation finish, and in between it is austenite and bainite. Okay, and here you can see this line indicates M star. This M indicates the martensite. M indicates martensite. Martensite. SITE. So martensitic start occurs at this point, and this is where the martensitic finish line. So martensitic start and martensite finish. Okay, austenite will start transforming martensite, and austenite will completely transformed into martensite. These two may indicate. So three different types of phase, two non-equilibrium phase transformation you can see, this bainite, martensite, and that is why we have not seen this kind of transformations, this kind of phases in the equilibrium phase diagram. We have only seen the pearlite, which is the equilibrium phase. Now can you tell me that if the carbon percentage is less than 0.76%, then what will be this phase? Instead of pro-eutectoid phase cementite, that phase will be the ferrite, but the curve will be similar to this one. So what you can see is that in austenite, depending upon the cooling rate, it is possible that we can get different kind of structure, like pearlite, and again pearlite can be fine pearlite, it can be coarse pearlite. We can get at moderate cooling, we can get bainitic structure, and bainitic structure again can be fine bainite, it can be coarse bainite. We can get martensitic structure if we rapidly quench it, and then basically I have already told you that martensite is very hard and brittle. That's why to make it in use we have to reheat it, which is called the tempering, and we can improve some of the ductility and we can use it. Here you can see the coarse pearlite structure, and here you can see the fine pearlite structure. Okay, spheroidite is another kind of phase that you will observe if you heat the pearlite for a prolonged period at around 600-700 degrees centigrade. If you heat it for a very long time, then you will find that fine spherical ball-like cementite are producing within the ferrite matrix. Okay, so alternate layers laminar structure will break, and ultimately this kind of spherical balls or cementite you will observe in the ferrite matrix. And this is a very soft kind of a steel and can be easily machined. And to make the steels machinable, many times by heat treatment we convert it into spheroidite, and after machining we do the proper heat treatment to retrieve the other properties. So spheroidite we'll discuss in the next part of the phase transformation in detail again. So let us just see this particular phase is also present. And one question is there: why do spherical shapes dominates at the end? The reason is very simple. The spherical shapes actually reducing the surface area, and that is why it reduces the energy. So ultimately any stable state that you are getting are producing because they are reducing the overall free energy. Here basically the surface energy is reduced by forming the spheres. So that is basically dominates. Now the bainite structure, here you can see as the bainite structure observed, if you cool it very fast up to say temperature less than 500, say 450 or something like that, and then if you maintain the temperature for a long time, then what you will observe that bainitic transformation takes place. Since this is happening at a very low temperature, so very fine structure will be formed, and so bainite is a very fine needle-like cementite you can see. So no longer here in the phase form it is the ferrite and cementite is present, but it is not in a laminar structure like pearlite. It is a bainitic structure, it is not a laminar structure that pearlite has. You can see the cementites are now in the form of needles in the ferrite matrix. Okay, so these kind of structures you will get in the bainite. So very fine structure, so in terms of mechanical properties definitely it will be stronger than the even fine pearlite. Okay, so bainitic structures, I have already told you, is a needle-like structure, and small cementite particles are also present, and this is what is called the acicular bainite. Okay, so this is basically much finer at a lower temperature, occurs lower level, and bainite transformed to iron and cementite with sufficient time and temperature, considered semi-stable below 150 degrees centigrade. Anyway, so you have just try to remember one thing, that this happens at a temperature range less than 500 degrees centigrade, maybe up to 400 450 you get this bainitic structure. Okay, and these are very fine structures, needle-like cementites are present in the ferrite matrix. Now the spheroidite structure, I have told you just that if you heat it for a very long time, that means if you keep it for a very long time at a particular temperature, then what will form, that ultimately this spheroidite structure will remain. Okay, so it is, you can see in the time range it is there, you can see that the large time is required, and if the pearlite is remained for a very long time, then it can convert it into spheroidite. Okay, here you can see the spheroidite, pearlite still partially transformed into spheroidite, not completely. Some of the regions here you can see that some of the spheroidite structures has been formed. The martensite transformation occurs when, if you quench it very fast, you can see this is the line. That means within a very short period of time you are reducing such a high temperature from 800 to say 100 degrees centigrade. So if the cooling rate is very high, then you can suppress this transformation like pearlite or bainite transformation, and then what will happen? The martensitic transformation occurs. So austenite is a phase, martensite is another phase, and what happen, actually you are cooling it so fast that you are not allowing any time, so this carbon will not get time to diffuse out of the structure, and that is why they still there within the structure, and obviously the residual stresses will be present within the material, so there is a chance that chances of thermal cracking is also there, and these are very hard and brittle, because you know that only the space that is there within FCC at a very high temperature is maximum up to few percentage only, and but a lot of carbon atoms are still there at a very low temperature. That means obviously it will be highly stressed condition. So very hard and brittle phase that you will see in the martensite. So hardness increased very high, but to use it properly, after that tempering is required. Tempering is nothing, it is only that further this martensite is heated to a temperature say 250, 300 or 400, and then keep it for a few few seconds, few hours, depending upon the amount of ductility that you want to impart, and then you further cool it to room temperature. So by this tempering you can induce some of the ductility, so that the toughness can be increased and it can be used. Here you can see there are two different kinds of martensites. Here you can see the martensites are in the form of laths. Laths are like rod or steel rules, this kind of thing. These are called laths. Okay, this kind of a structure, and these are like plates. Okay, so both the structures are possible, and in high carbon steel you will get this kind of plate like structure, in the low carbon steel you will get this kind of a structure. So some of the important takeaway points regarding martensite: without martensite transformation occurs without composition change. Okay, that means you can see the composition remains same, carbon is not going to diffuse. Okay, it's a single phase, and the transformation occurs by shear without need for diffusion. There is no need for diffusion, that is the most important thing. Only because of the shear, the changes in the structure, like crystal structure from FCC, it converted into BCT. Okay, and the atomic movements required are only a fraction of the interatomic spacing. Okay, so atomic movements are very small. The amount of martensite formed is a fraction of the temperature to which the sample is quenched, and not of time. Okay, so it's a very fast cooling process, and because of which the martensite form. Hardness of martensite is a function of carbon content. Remember that if the carbon content is more, then that martensite will be more hard. Okay, but the high hardness steel is very brittle, as the martensite is brittle. Okay, and steel is reheated to increase its ductility. That is very important. Reheat it and keep it for a time, so that the carbon can diffuse out in the form of particles and impart some amount of ductility, and this process is called tempering. Okay, here you can see what are the different types of phases present, like pearlite in this region, bainite in this region. Here it is unstable austenite. Okay, and martensitic start. These are the important transformation that we can see. Now, for example, that iron carbon alloy is there, suppose eutectoid composition. The question is, specify the nature of the final microstructure. Okay, that means the percentage of bainite, martensite, pearlite and all that for the alloy that is subjected to the following time temperature treatment. Suppose alloy begins at 760 degrees centigrade and has been held long enough to achieve a complete and homogeneous austenitic structure. That means suppose it is at a 760 degrees centigrade and hold long, so that now it is completely austenite. Now the question is, if it is rapidly cooled to 350 degrees centigrade and hold it for 10 to the power 4 seconds, so rapidly cooled to 350 degrees centigrade, that means this position you can see, and then hold for 10 to the power 4 seconds, up to 10 to the power 4 seconds. If you keep it at that temperature, so what will be the final structure? So final structure will be 100% bainite. As simple as that. Second part, and quench to room temperature. So after converting 100% bainite, if you quench it to room temperature, that means if you put it into the water and wait for coming to the room temperature, then you will find that the 100% is bainite, because it is already transformed to bainite. Okay. Another example. Suppose you rapidly cool to 250 degrees centigrade and hold for 100 seconds. Now you cool to 250 degrees centigrade and hold for 100 seconds, up to 100 seconds. You see, now you are in a position, you are not touching the bainitic start, and quench to room temperature, and now you quench to room temperature. But here you see the bainitic transformation will not occur, but martensitic transformation occur. Because the thing is, it is austenite, unstable austenite. Now if you are quenching it, it will cross this line and this line, that means 100% martensite occur. Previously what has happened, that the whole austenite has been converted into 100% bainite. There is no more austenite that is to be converted into martensite. So now if you are quenching it, there is no austenite that will be converted into martensite. So 100% bainite will remain there. Another problem, suppose you rapidly cool to 650 degrees centigrade. You rapidly cool to 650 degrees centigrade. Then hold for 20 seconds. Maybe if you hold it for 20 seconds, you can see this is 10, this is 20 seconds. And rapidly cool to 400 degrees centigrade. Rapidly cool to 400 degrees centigrade here. You remember, at this position what is there? 50% of the austenite will be converted into pearlite, and the remaining 50% austenite is still there, that has not yet been transformed. Now you rapidly cool to 400 degrees centigrade, and hold for 10 to the power 3 seconds. Now if you hold for 10 to the power 3 seconds, then at 10 to the power 3 seconds, what will happen? Remaining 50% portion of austenite will be converted into bainite. So what will be the final structure? So now the whole austenite, 50% already pearlite and remaining 50% into bainite. There is no remaining austenite. So now if you quench it to room temperature, your final structure will contain 50% bainite and 50% pearlite. Clear? So now let us try to solve these problems. That suppose you heat at 820 degrees centigrade, that means you have actually austenized it. Now quench to 650 degrees centigrade and hold for 90 seconds. You observe in the diagram. Remember, this is not a Eutectoid steel, this is 1045 steel. 1045 steel is what? It is carbon percentage is, this is a 10 indicates it is a plain carbon steel. And this 45 indicates 0.45% of carbon. 0.45% of carbon. 0.45% of carbon means hypo-eutectoid. So hypo-eutectoid steel. That means the hypo-eutectoid steel. If this is corresponding to 0.76, this is hypo-eutectoid steel. 0.7, 0.45. Okay, so what will be the pro-eutectoid phase? The pro-eutectoid phase will be ferrite. Okay, so pro-eutectoid ferrite phase will be there. So the diagram will be like this. Here you can see this is the pro-eutectoid ferrite phase, and here it is the pearlitic start, pearlitic finish, bainitic start, bainitic finish, martensitic start, martensitic finish. So this is what is the diagram. Now in this diagram you have to basically show you have to draw these cooling curves and finally conclude the microstructure. So you at quench to 650 and hold for 90 seconds and quench to 25, that means at room temperature. So at 650 degrees centigrade means why? This is 600, this is 650. So at 650 degrees centigrade, you quickly reach from 840 to 650 degrees centigrade. Suppose you come to this position, and then what you did? Hold for 90 seconds. Where is 90? This is 100 seconds, right? At 650, 90 seconds means 90 seconds means maybe here. So you are here. And then you come to 25 degrees centigrade, maybe the room temperature. So in this process 100% pearlite will be transformed at 650 degrees centigrade. Clear? But obviously before that ferritic transformation will take place. So austenite will be transformed into what? Fe3C, Fe alpha ferrite and pearlite. Alpha ferrite and pearlite. Okay, so here you see the ferritic transformation, then pearlitic transformation. Okay. Similarly, at 820, the second problem we can do quench to 450 degree, hold for 90 seconds, quench to 20. So 450, then hold for 90 seconds and quench to 20. That means it is 100% bainite. You see, in this case there will be no pro-eutectoid phase will be there. There will be no pro-eutectoid phase. Here you can see the pro-eutectoid ferrite will be there only up to this temperature. Only up to this temperature. Below which there is no pro-eutectoid phase. This is bainitic start and this is bainitic finish. So it is 100% bainite. Okay. Similarly, the other problems you can see 820 degree and quench to 25. So it is martensite, 100% martensite. Quench to 650, hold for 100 seconds and then quench to 25 degrees centigrade. Okay, so 650, 100 seconds. 650 is here. 100 second is here. 650, 100 second. So it will contain ferrite and pearlite, pro-eutectoid ferrite and pearlite. Quench to 720, hold for 100 second, quench to 400 degree and hold for 500 second and quench to 25 degrees centigrade. Quench to 780. Okay, 780. What? 780. Sorry, 680. Quench to 720. Okay, quench to 720 means almost here. Then hold for 100 seconds. 720, hold for 100 seconds. That means you are at around 50% conversion of the pearlite. Okay, not completely converted into pearlite. So it is alpha ferrite plus 50% pearlite, and then what is done? Quench to 400 degrees centigrade and hold for 500 seconds. Quench to 400 degrees centigrade and hold for 500 seconds. Quench to 400 degrees centigrade from here, as if 400 degrees centigrade for 500 seconds. 100, so 500 seconds. So remaining portion will be bainite. Pearlite, 50% pearlite and 50% bainite. So alpha ferrite will be there, and the remaining portion will be divided into pearlite and bainite. Similarly, the last one, 720 degrees centigrade, hold for 100 seconds, quench to 400 degrees centigrade and hold for 10 seconds only. Now instead of 500 seconds, it is hold for 10 seconds. That means even the bainite will not be converted completely, and the remaining 50% bainite, 50% of that will be converted into bainite. And if you come to room temperature, so that portion will be converted into martensite. So alpha will be there, some amount of pearlite will be there, and the remaining portion again divided into bainite and martensite. Okay. Quench to 25 degrees centigrade, heat to 500 degrees centigrade and hold. Finally the quenching will produce the martensite, and then heat to 500 degrees centigrade. That means now your tempering at a 500 degrees centigrade and hold for a long time will basically give you, if you hold it for a very long time, it will give you the spheroidic structure. Okay. Generally spheroid occurs at a very high temperature, close to 600, 650. At 500 degrees centigrade, what will happen, that from martensite, basically some of the carbide particles or the cementite will form within the martensite. So remaining portion will be martensite, and some of the carbides will form like this. All these is not going to form like ball-like structure, but some of them will be fine. This kind of a structure will be formed. Okay. We'll see in the next part of the phase transformation. This particular structure is called sorbite. Okay. So anyway, this kind of formation is expected. But if you hold it for a very long time, at a 500, 600 degrees centigrade, 600, 650 degrees centigrade, you may get the spheroidic structure. Now finally, the strength with the change of microstructure is quite visible by the time. You can see that if the transformation temperature gradually decreases, then the strength of the material is gradually increasing, gradually decreasing. That means if the transformation occurs at 700 degrees centigrade or 675 degrees centigrade, those are basically pearlitic structure. Okay, the pearlitic structures are respectively softer structure, tensile strength is less. Okay, but gradually if you reduce less than 500 maybe, you will see the bainitic structure will form. So, and the bainitic structure, you see the strength is very high. Okay, those are hard material. In the martensite, finally you will find that it is very, very hard material, high strength material. But in terms of ductility, you see ductility is very low in martensite, and in the bainite the ductility is gradually increasing with respect to martensite. But if you compare with pearlite, that is not so good ductile. Okay, you can see the pearlite is much more ductile if you compare with respect to bainite. Okay.